Okie dokie, we're back and we are here to work on problem set 34. You can see here on the right I've got that same chart with my different Q equations just because I'm trying to emphasize the fact that these are all we've ever used, regardless of the fact that some of you might not believe me. So let's jump in here and answer some of these conceptual questions. Alright, what is calorimetry? So in previous problems we have been setting up this Q equals negative Q thing. Essentially all that's doing is saying the heat of one thing is related to the heat of the other thing. They're related by being equal. And so by knowing information about the change of heat of one species, then we can use that knowledge in order to learn about a different species. So maybe we know the change of heat of a certain amount of water. We're trying to find the heat capacity of iron, like we did in one of the problems on problem set 34. Right, we can use information about one thing to find information about another thing. Calorimetry is kind of the fancy name for the very scientific way of doing this. Basically in calorimetry, we use a very isolated system where, I'll just explain it. Basically, a bomb calorimetry specifically, you've got this container and it's got a little dish in it. And the dish is concealed in this thing, and there's like something around it, probably water. But essentially you've got this big box, and then you put your stuff in here that you want to learn about, and you burn it. Whoa. This is water. And you burn it. And when you burn it, it releases heat. That heat is absorbed by the box. And because we know the specific heat or the heat capacity of the box, we can learn something about the heat that was released from the thing that I burned. Okay, so this specifically is a bomb calorimeter, but we're going to be doing the same things that we're doing before with Q equals negative Q. It's just one of our Q's is going to be the Q for the calorimeter, which is an object. Therefore, we'll most likely be using the Q equals capital C delta T. But it's just the same thing we've been doing before, but now it's more specific, and this is how you would do measurements in an actual lab. Why is it necessary to know the heat capacity of the calorimeter? Well, it's necessary to know the heat capacity of the calorimeter because we're going to have Q calorimeter equals negative Q of some reaction that's going on inside. Usually we want to learn about the reaction. And if we want to learn about the reaction, we need to know everything about the calorimeter. And one of those things, C delta T, right? One of those things is going to be the heat capacity. So that's why it's necessary to know the heat capacity calorimeter. If you went out to the store and bought a calorimeter, you would, I don't know where you would go to buy one, but if you did, I'm sure that it would come with specifications about what its heat capacity is. Cool. All right. Why do we use the heat capacity, Cp, instead of the specific heat or molar heat capacity to describe the heat capacity of the calorimeter? That goes back to what we're talking about over here. Specific heat is per gram, molar heat capacity is per mole, just normal heat capacity is just kilojoules per degree Celsius. Why? Because we don't need to specify the number of grams, we don't need to specify the number of moles. A bomb calorimeter is literally an object. You can't have different amounts of it, and so we just absorb that M and C together. We use a big C because it's just an object. When measuring the heat of combustion of a very small amount of material, would it be better to use a calorimeter having a heat capacity that is small or large? I would argue that it's better to use a calorimeter that is a small heat capacity, because if we're only burning a small amount of material, then we're only releasing a little bit of heat. So if we want to get a good measure, we need a big temperature change from a little bit of heat, and that is consistent with a small heat capacity. So I believe that small makes the most sense. All right, so now let's do some calculations. Calculate the heat capacity of a calorimeter in the combustion of 4.663 grams of benzoic acid. Produce to increase the temperature 4.179 degrees Celsius. This seems like they don't give us very much information, right? Remember, there's some information, though, that on homework, they just expect you to look up. On a test, you'd have to be given a little bit more information than this. But let's just set up the problem and see what we need. So, heat capacity of a calorimeter, if the combustion of this much benzoic acid produces an increase in temperature of that much. Is that the increase in temperature of the benzoic acid? The benzoic acid just changing temperature? No. Benzoic acid is combusting. So then what's changing temperature? The calorimeter. Because the combustion is happening inside the calorimeter. So the calorimeter is going to get warmer. So we know that we're going to have the Q of our reaction. I'm going to say combustion. That's what's happening to the benzoic acid. And that's going to be negative Q of the calorimeter. Well, if we're combusting benzoic acid, which category does it fall into? Is it a temperature change or is it a phase change / reaction? Well, we're combusting it, so that's going to be a phase change / reaction. So I'm going to replace Q combustion with N combustion delta H combustion. It's going to be negative, and what's happening to my calorimeter? It's changing temperature, so it's going to be an MCAT type equation. But again, it's an object, so we're just going to use big C. And remember that big C is just in kilojoules per degree Celsius, so I only need to multiply by degrees Celsius to get my Q. Okay, do I know how much benzoic acid I'm burning? Yeah, I've got 4.663 grams. Do you know the delta H of combustion of benzoic acid? They don't give it to me. Remember, if you've got a C or a delta H that they don't give to you in a problem, you can look it up. This is a weird one. This is one that they wouldn't typically expect you to look up. I don't know why they do here. But looking it up, I get that the delta H of combustion of benzoic acid is 26.38 kilojoules per gram. So that's my delta H of combustion. Just looked that up. By look it up, I mean Google it. And then, do I know the heat capacity of my calorimeter? That's what I'm looking for. Do I know the change in temperature of my calorimeter? Yes. So I know that I wrote N here, but N usually means moles, but I'm going to use grams. Why? Because I got the heat capacity in grams. So 4.663 grams, 26.38 kilojoules per gram equals negative. I'm looking for the C of the calorimeter, and I know that I'm increasing the temperature of 7.149 degrees Celsius. Okay, looking at this, there's one thing that I messed up on. If you can catch it, what is it? Well, when I looked up the delta H of combustion, it gave me a positive value, but I know that it's burning, and so I know it should be releasing, so I should have a negative value there. And the reason that I caught that is that when I actually plugged these numbers into my calculator, I got a negative heat capacity for my calorimeter, which doesn't make any sense, right? If I put heat in, the temperature can't go down. So I need a positive heat capacity, and so that's what helped me catch that. I got the C of the calorimeter is 17.2. And what are the units going to be here? Well, I had grams cancel with grams, so I had kilojoules on the left, and I divided by degrees Celsius. So I should have kilojoules per degree Celsius, which is consistent with what the units should be for the heat capacity of a calorimeter. All right, let's keep going. This one's pretty short. Okay, the aromatic hydrocarbon cymene is found in nearly 100 spices and fragrances, including coriander, anise, I think it's anise, and thyme. The complete combustion of this much cymene in a bomb calorimeter, they give you the C of the calorimeter, produces an increase in temperature of 19.35 degrees. How much thermal energy is produced during the combustion of 1 mole of cymene? All right, so I'm burning cymene in a bomb calorimeter, so I'm going to get the Q of my combustion equals negative Q calorimeter. Combustion is a reaction, so I've got N combustion delta H combustion. That's going to be my equation for Q of combustion. My calorimeter is changing temperature, and it's just an object, so I'm going to have negative C cal delta T cal. Do I have the amount that I'm burning? Yep. Now this says 1 mole. We'll talk about that later, but that's not how much I'm burning. How much am I burning? Burning 1.608 grams. So I have my amount. I'm looking for delta H of combustion, how much thermal energy is produced during the complete combustion of 1 mole. So that's what I'm looking for. I have Ccal and I have delta Tcal. So I'm just going to plug these in. 1.608 grams. I'm looking for delta H combustion. 3.64, and that's kilojoules per degree Celsius. And I'm increasing the temperature 19.35 degrees Celsius. So I can plug all this in. And I got that the delta H of combustion is negative 43.8. Is that the answer? The answer, no, it's not the answer. Why? What are the units here? I've got kilojoules on the right side, because Celsius cancels, divided by grams on the left side. This means is when I burn 1 gram of cymene, I release 43.8 kilojoules of energy. That's awesome, and that's true, and that is a perfectly valid delta H of combustion. But it wants to know how much thermal energy is produced during complete combustion of 1 mole. This is per 1 gram. Well, I can convert that. I could say negative 43.8 kilojoules per gram, and I know I have the formula for cymene, so I could find the molar mass, and I get that 134 grams is 1 mole. So if you see now, what are my units? Kilojoules per mole. So when I plug that into my calculator, let's see if I got it right. Yep. Okay. Delta H of combustion is now negative 5869.2. My units are kilojoules per mole. So that's how much. I could have also just said negative 5869.2 kilojoules, because it says how much is produced during complete combustion of 1 mole. So I don't need to write the per mole, because that's what the question's asking. So if I just wrote kilojoules, I'll be fine. But the answer should be the same. All right, on to number 5. The flavor of anise is due to anethol, a compound with a molecular formula of C10H12O. Combustion of 1 mole of anethol produces 5541 kilojoules of thermal energy. If 0.95 grams of anethol is combusted in a bomb calorimeter with that heat capacity, what's the change in temperature? All right, hopefully you're starting to notice that calorimetry is just like what we were doing on problem set 33, but it's only like one type of problem. It's one specific scenario where you're running a reaction in the object that's changing temperature. So we've got Q of combustion. I'm going to put the negative over here, just mix it up. Equals Q of the calorimeter. So negative Q combustion equals Q of the calorimeter. So negative N combustion delta H combustion equals C calorimeter delta T calorimeter. Do I know how much anethol I'm burning? Yep, 0.95 grams. Now it says 1 mole right here. Is that how much I'm burning? No. That tells me that when I do burn 1 mole, I get 55.41 kilojoules of energy. What is that? That tells me the delta H of combustion. That delta H, I could actually write this, that delta H is 55.41 kilojoules per mole. Then I'm given the heat capacity, so I can get delta T. So I'm going to quickly change my 0.95 grams. Because this 5541 is in per mole, I want to change this to moles. So gotta get the molar mass. Molar mass I got was about 148 grams per mole. So then I have 0.95 grams, 148 grams per mole. Okay, so I get negative 0.00642 moles. My delta H, again, is negative 5541. I know that it's negative because it's burning, so it must be releasing heat. 7.854 kilojoules per degree Celsius. And my change in temperature is, what happens? Oh, that's what I'm looking for. I'm looking for how much, what's the change in temperature of the calorimeter. Okay. See if I did that right. Okay, so I get the change in temperature of the calorimeter is positive 4.529. Again, does the sign make sense? Yes, the sign does make sense. I'm burning something inside the calorimeter. It should get hotter, so the change in temperature should be positive. Okay, 4 grams of ammonium nitrate. The active ingredient, some chemical cold packs, is dissolved in that much water. Temperature of the resulting solution is that, is that much colder than the water and ammonium nitrate were before they mixed together. What's the value of delta H for the following dissolution process? Then it says you can assume the heat capacity of the final solution is just this heat capacity of water. Is the final solution water? No, it's this water plus the stuff we dumped in. So what are we doing here? We've got a thing of water. We take our ammonium nitrate, which is probably like a powder or crystal. We drop it in, and the whole thing gets colder. Okay, the whole thing gets colder. So this has nothing to do with bomb calorimeter. Okay, this is just heat transferring. So what are my two things going on? Well, I know I have water. And what is changing the heat of the water? Well, there's this dissolving going on. This ammonium nitrate is going from solid to aqueous. Okay, it's written out like a reaction. So I'm going to write Q reaction. That's what RxN is, reaction. You could also write Q phase change. So it doesn't matter, right? Because the equation for a reaction and a phase change are the same. So, and we're trying to find the delta H of this reaction. All right, what's happening to my water? Well, it's changing temperature, so I'm going to have an M water, C water, delta T water. Negative, what's happening? I've got a reaction. I'm going to have N reaction, delta H reaction. And what's the value of delta H? That's our goal. So do we have the mass? Oh, my mistake. Backtrack here. Is it the water that's changing temperature? Well, the water is changing temperature, okay, but they tell us the temperature of the resulting solution has gotten colder, and the heat capacity of the solution. So it's actually not water here. What is it? It's the solution. Because the whole thing, the solution being the water plus the powder that I added. So this is M solution, C solution, delta T solution. Sorry about that. Okay, do I have the mass of my solution? Yes. What is my solution? It's my water plus my ammonium nitrate I added to it. So my mass is 100 grams. Specific heat of my solution, they tell me it's the same as water. Change in temperature of my solution, it gets 3.07 degrees Celsius colder, so it needs a negative. Equals negative, and then how much stuff did I react? Well, 4 grams. Usually delta H's are kilojoules per mole though here, so I'm going to change that 4 grams to moles real quick. So it's just going to be 4 grams divided by 80.04 grams per mole times delta H of my reaction. I can plug in numbers, do some math. Let's see. And golden. All right, I got the delta H of that reaction is 25702 joules per mole. Should it be positive? Is this reaction endothermic? Yes. How do I know that? Because when the reaction happened, the solution around it got colder, which means that the reaction must be pulling in heat, which means it's endothermic, which means it should be positive. All right, hopefully this helped with your understanding of calorimetry and how to set up these problems. Look for more videos coming up for problem set 35 and 36.